Hello, everyone. Welcome to the ILTA Physics online problem solving lecture. The problem we are going to solve today is about projectile motion. Simply put, projectile motion is a combination or a superposition of constant velocity motion and accelerated motion. Imagine kicking a ball toward the sky at an angle, as shown in the diagram below. The path the ball follows through the air is projectile motion, and we are going to analyze that movement. As I mentioned, projectile motion is a combination of two types of movement. To be more precise, in the horizontal direction, the object undergoes inertial motion, moving at a constant speed without any change in velocity. In the vertical direction, it performs free fall motion, which is an accelerated motion where the velocity changes due to the gravitational acceleration. I use the term inertial motion for the horizontal direction. The inertia is an important concept we will dive into in the next chapter. For now, just think of inertial motion as an object continuing to move exactly as it was, without changing its speed or direction. The types of problems we will solve today include projectile motion launched horizontally from a certain height, motion launched upward at an angle, and cases where an object is launched downward at an angle. Since projectile motion is a crucial part of two-dimensional kinematics, I hope you organize and understand these concepts well according to each problem type. First, let's briefly summarize the basic principles of projectile motion. Projectile motion occurs when an object in a two-dimensional plane travels along a parabolic path. As you can see in the diagram, you can think of it as an object moving forward while gradually rising, reaching a peak, and then coming back down. I already explained the concepts and formal derivation of the physical formulas for projectile motion in detail during my theory lecture. So here, I will focus on a brief summary of the equations we use for problem solving. Since this is motion in two dimensions, we can divide the object's movement into the x-axis and y-axis directions and analyze each one independently. The most important physical concept to understand here is that once the object is launched at an angle, the only physical factor affecting its motion is the gravitational acceleration, which acts vertically downward. Now let's analyze projectile motion kinematically. To analyze any motion, we must first establish a coordinate system and an origin. Since this is 2D motion, we will set up a Cartesian coordinate system and set the object's initial position as the origin. To clarify, setting up a Cartesian coordinate system means we define the rightward and upward directions as positive. This is very important because it determines the signs of the values we use in our calculations. Now, let's look at the motion. If an object starts its projectile motion with an initial velocity represented by the green arrow, we can use trigonometry to break this initial velocity vector into horizontal and vertical components. Specifically, the horizontal initial velocity is the magnitude of the initial velocity times cosine theta, and the vertical initial velocity is the magnitude times sine theta. First, let's analyze the horizontal motion along the x-axis. Since there are no other physical forces acting horizontally on the object once it starts its flight, it moves at a constant velocity without acceleration, called uniform motion. In uniform motion, the position of the object can be calculated as the initial position plus the product of velocity and time. Next is the vertical motion. While the object is moving, the gravitational acceleration constantly acts toward the center of the Earth, that is, in the downward direction. Therefore, we can analyze this as free fall motion or accelerated motion with a constant acceleration. Since it is accelerated motion, the acceleration is the gravitational acceleration, which is negative 9.8 meters per second squared. And the vertical initial velocity is the magnitude of the initial velocity times sine theta. The reason the gravitational acceleration is negative is that we set the upward direction as positive in our coordinate system. The remaining equations for vertical motion are the same as those for free fall. The final velocity equals initial velocity plus gravity times time, and the final position follows the standard formula for accelerated motion. Now, for the rest of the diagram. Because the vertical part of projectile motion is essentially free fall, the tips we use for solving free fall problems apply here too. Number 1. The hang time, or the time the object stays in the air, is determined solely by the vertical free fall motion. If the starting and ending heights are the same, the total hang time is exactly twice the time it takes to reach the peak. Number 2. When the object is at its highest point, its vertical velocity is 0. Number 3. When the object is at the same height, the upward speed and the downward speed are equal in magnitude but opposite in direction. Finally, a common question in projectile motion concerns the magnitude and direction of the velocity at a specific position or instant. For example, to find the velocity at the landing point, you calculate the x and y components of the velocity at that spot separately, and then use them to find the overall speed and angle. Now let's solve some projectile problems together. Problem number 28 is a classic, basic type of projectile motion. A ball is launched horizontally at 1.25 meters per second from a height of 1 meter. The question asks how long it takes to reach the floor and what the horizontal distance traveled is. First, let's set up a Cartesian coordinate system and set the initial position of the ball as the origin. This is the spot marked in yellow in the diagram. We will think of the x-axis and y-axis motions independently. Breaking down the initial velocity, the x-axis velocity is a constant 1.25 meters per second. The y-axis initial velocity is 0, making it a free fall motion starting from rest. As explained, the flight time is determined by the vertical motion. Let's look at the y-axis position when the ball hits the floor. Since our origin is the starting point and the ball moves 1 meter downward, the y-coordinate at the end is -1. Using the position formula for accelerated motion, the final position is -1, the initial y-velocity is 0, and the gravitational acceleration is -9.8. Solving this equation gives us a time of 0.45 seconds. Now let's calculate the horizontal distance. Since the horizontal motion is constant velocity at 1.25 meters per second, the distance traveled in 0.45 seconds is 0.56 meters. This is the most fundamental type of projectile motion. If you understand the right formulas for each direction and the signs dictated by the coordinate system, it's easy to solve. Problem 31 is a typical example of an object launched upward at an angle. A lion can jump to a maximum height of 3 meters and cover a horizontal distance of 10 meters. We need to find the magnitude and angle of the lion's initial velocity. If you can visualize the projectile motion shown in the diagram, you're already halfway there. Also, remember that the vertical velocity at the peak is 0 and the total hang time is twice the time to reach the peak. First, set the coordinate system and origin. We'll use a Cartesian system with the origin at the lion's starting point, the yellow dot. In this case, we need to find the initial velocity given that the maximum height is 3 meters. Vertical motion is free fall. Since we don't have information about time yet, we can use the formula relating velocity and displacement to find the initial y-velocity. Thinking only of the vertical motion, the final velocity at the peak is 0, and we plug in -9.8 for gravity. Calculating this gives an initial vertical velocity of 7.67 meters per second. The positive value confirms the lion is jumping upward. Always keep the signs and directions in mind. Now we can find the time it takes to reach the peak using three different formulas. Any of them will give the same result. The simplest way is using the relationship between average velocity and displacement. The initial velocity is 7.67 and the final velocity at the peak is 0. Plugging these in shows it takes 0.78 seconds to reach 3 meters. The second way is using the final velocity formula with gravitational acceleration and initial velocity, which also gives 0.78 seconds. The third way is using the displacement formula for accelerated motion, which yields the same result. I recommend practicing with different formulas to get comfortable. Now let's calculate the horizontal motion. The horizontal velocity remains constant throughout. Since it took 0.78 seconds to reach the peak, it takes another 0.78 seconds to fall back down, making the total time 1.56 seconds. In constant velocity motion, distance equals velocity times time. Substituting 10 meters for distance and 1.56 seconds for time, we find the horizontal initial velocity is 6.37 meters per second. Now we have both the horizontal and vertical components of the initial velocity. Let's find the total magnitude and the launch angle. The magnitude of the initial velocity is the square root of the sum of the squares of the components, which comes out to 9.97 meters per second. The jump angle is the inverse tangent of the y component over the x component, which calculates to 50.3 degrees. One more thing to note about projectile motion. If the launch and landing points are at the same height, the initial and final velocities share a specific relationship. The x components are the same. The y components have the same magnitude but opposite directions, and the angles are equal. Visually, the initial and final velocity vectors have the same size but are reflected. This is a classic angled launch problem. Make sure to review this carefully to fully understand it. Problem 35 involves an object launched downward at an angle. An object is thrown from a height of 6 meters at a speed of 12 meters per second, at an angle of 30 degrees below the horizontal. We need to find the horizontal distance traveled. We'll set the Cartesian coordinate system with the origin at the starting position of a soccer ball, the yellow dot. Since we are given the magnitude and angle of the initial velocity, let's break it into horizontal and vertical components. Be careful here. The launch angle is -30 degrees. In our coordinate system, counterclockwise is positive, so 30 degrees downward is -30. Therefore, the horizontal initial velocity is 10.4 meters per second, and the vertical initial velocity is -6 meters per second. The vertical distance to the ground is 6 meters. Using the position formula, the time it takes to hit the ground is 0.69 seconds. Note that the final vertical position is -6 because it is 6 meters below our origin. Finally, we just need to find how far it traveled horizontally during this time. Since horizontal motion is constant velocity, we multiply the horizontal velocity by the time, which gives us 7.17 meters. Projectile motion is just constant velocity horizontally and free fall vertically, so the formulas shouldn't feel brand new. However, to solve problems accurately, practice setting up your coordinate system and origin correctly. And be very careful with the signs for position, velocity, and acceleration. That's it for today's lecture. Great job, everyone. I'll see you next time.